have 4 faculties more than us. So that must be the reason that you are in the top. I'm just kidding. Okay. So as far as science and medicine is concerned, I think we are ahead than the Ferrari University. Oh, sorry. Right. So we have doing a lot of work, connected to all the avenues. But for this short presentation, I just selected nanohydroxyapatite and their composites, different facets of usage. As Professor Gamini Rajapaksa mentioned, and he had done a lot of work on HAP, and hydroxyapatite is I think if you look at, yes, hydroxyapatite is the main inorganic constituent in bones and in teeth of all vertebrates. And therefore, you can consider that one as one of the key materials to sustain life on Earth. And inherently it has all the features necessary for a biomaterial. So all the features are mentioned here, and I think there are so many research going on with hydroxyapatite, and we also consider it as one of our best materials, and a lot of my students, PhD students, are working on hydroxyapatite, and because of this biocompatibility, we are working on the hydroxyapatite in water purification. Our main target is for the yes, this is for this little presentation, the different facets of hydroxyapatite, as far as our research is concerned, can be categorized as in water remediation, nanohydroxyapatite and its composites for water remediation and for biomedicine. So why I'm looking at water remediation? And Dr. Gamini Kumar Singh also mentioned in the morning, there are so many burning issues in the world. One of the main issues is the water pollution and pure drinking water. We are suffering, not only the Sri Lanka, but if you, as a whole, in the world, the polluted drinking water is causing a lot of health effects. And in Sri Lankan context, if you look at, it is not necessary to tell you about the diseases that we are getting out of water pollution. You name any disease, it has a connection to polluted water. If this is, anything can crop up with polluted water. So the water is getting constantly contaminated during these pollutants, because of these pollutants. So it's very important to get rid of this pollution. And in Sri Lankan context, I'm from Sri Lanka, so we are looking at this, even though there are so many problems, if you look at this is chronic, there is a alarming health condition or health problem in Sri Lanka. This is known as chronic kidney disease of unknown etiology. And if you look at, this is particularly disturbing because there are, 22,000 deaths due to this disease for last 2 decades. So it's so disturbing, and we, as scientists, we should do something for this one. And so then, and if you look at the main cause for this one, because 20% of the rural population, they depend on the groundwater. So sometimes some elements that are geogenic in origin can affect their health very badly. It has been identified out of those elements. I think Professor Rajapaksa, I should say that you are the one of the pioneers to tell that it is fluoride. The fluoride has been identified as one of the main culprits for this disease. So because these areas now, this particularly central province, Sri Lanka, so this area, they are groundwater, because they depends on groundwater. The groundwater is contaminated highly with fluoride. And now the recent science also, confirm those things. So it's utmost important to remove these pollutants from water. And when it comes to water purification techniques, if you look at, these are the common techniques, and Sri Lanka, we do all these techniques except for reverse osmosis and electrochemical methods. And out of these methods, our attention goes to the filtration, because filtration is it's the kind of, very low cost and very easy, simple device. So we got a big grant to do this particular task. So our attention is to develop point of use water systems or personalized water purification system. So for that one, we need to develop materials which can absorb these pollutants, especially even cadmium is one of the suspects, because like the Sri Lanka is wherever we are getting this disease is also rich agricultural zones. So they suspect is, and even cadmium is one of the culprits for this particular disease. So we need to get rid of all these heavy metals and all the other pollutants from water. So we kind of looking at the point of use water filters, and the one, now we will see what are our strategies. Our strategy here is to develop superfast sorbents. Why do you need superfast sorbents? Because we can't just wait for these water to be filtered for like 24 hours. And we are also looking at personalized devices. So if the quicker the sorbent material, we can make the device smaller and smaller. And so that's why we are looking at the super sorbent, biocompatible. That's why the HAP is the base product or the major component in our research. So now, in order to develop, we have done so many research, and so identify some of these are having these super fast or super sorbent properties. And so if you look at the biocompatible nano hydroxyapatite, so we develop metal-based composites, natural polymer-based composites, and clay-based composites, and activated carbon-based composites. And if you go through this one now, what I will show you is, I will show you what are the important materials that we have developed, and then we will go to the, see whether those are super sorbents. Right? So the first, I will go through the materials, hydroxyapatite composites that we have developed in our research group. And so first thing is natural polymer based. So for that one, we use carboxymethyl cellulose as the polymer, and then you can see we could manage to get a very spongy, very homogeneous structure of hydroxyapatite, and that is with carboxymethyl cellulose, and then chitosan, another biomaterial, a biocompatible polymer, and chitosan is exists in crab shells, and our student, PhD student Ruchira is working on chitosan, and also there is another student working on chitosan, and so their work is different. This is for the water purification, and this is a coral shaped structure, and then the sodium alginate. The beauty of this compound, the hydroxyapatite, when you are synthesizing hydroxyapatite with these natural polymers, you get very highly porous and super fast sorbents. And also we were kind of, amazed by this morphology. And so then we discuss about this is how we characterize each and every composite using characterization techniques like IR. I don't want to go to the technical details. And then also we characterize using XCRD, and also, so now, in order to get this, if you look at the surface structure, this coral shape, and they are uniformly distributed. So why it is so? So we just suggested a mechanism based on this. You can see now these polymers, if you look at these biopolymers, they do have chelating atoms. Okay, so these are kind of acting as a kind of ligand atoms, ligating to the calcium, and calcium is kind of immobilized in one or the specific sites. So the immobilization calcium, and when you add phosphate seek through, and then they get towards this sites. And so now, because of this calcium and phosphate, further calcium, free calcium can come to that one. So these are acting as nuclei center. So the growth happens on those particular specific predetermined phases. So that's why we are getting the very homogeneous like structures. So that's the argument, and we also kind of confirm this using computational modeling. So, and we publish this data. So citizen mechanism. So the same mechanisms can be suggested for carboxymethyl cellulose as well as for sodium alginate. And then that's the first one we used, so we synthesized natural polymer based. And the second one is the synthesis of hollow hydroxyapatites and its composites. My student Veromi will talk about that one in detail. And so that's, our strategy is to do, it's a kind of, we form the micelles, and so as to have some ligating atom on the surface, and so to have calcium on top of that one, and then with the phosphorus, calcium hydroxyapatite is now kind of sitting on the on this one, like on the surface of the micelles, and after washing step you get in the hollow hydroxyapatite kind of morphology. And this is we have characterized again using SEM data, and then you can see it has a extremely porous structure, and its XRD is HAP, hydroxyapatite, crystalline hydroxyapatite, without any calcination or anything. And so we kind of characterize it, everything using all these techniques, not necessary to go into detail about those things. And now if you look at the hydroxyapatite, then again we kind of, we fill those voids or the hydroxyapatites with iron oxide nanomaterials and various other oxides, metal oxides as well, because of the time I don't want to go into all the details, it's very difficult, right? So this is the structure. You can see the physical appearance of the hydroxyapatite with iron oxide. And if you look at the iron oxide, and you can see the SEM picture clearly shows the morphological difference between hydroxyapatite nanoparticles and the iron oxide nanoparticles. And this has been further kind of characterized using EDX data or SEM and so on. And then, so now I synthesize, like hydroxyapatite polymer based and then hollow hydroxyapatite. And now you can see the hydroxyapatite natural clay based composites. So as we say to clay based, now montmorillonite, I think Professor Rajapaksha has done a lot of work on montmorillonite. It's one of the layered structures so that you can expand the layers, so that you can incorporate some other materials inside that one, and very biocompatible, and it has silica and alumina sites and all these things, so very good at absorbing all these pollutants from water, and also cheap material. So we just wanted to see, we want to get higher efficiency of MMT towards these the pollutants. So this is you can see this is the neat one, and then we modified with hydroxyapatite in 2:1 ratio, and then 1:1 ratio, and you can see more. Here there's no hydroxyapatite. You can see and here the morphology of the hydroxyapatite is very much different than when you use the polymers, because it's just a plate-like hydroxyapatite has been formed on top of this montmorillonite clay. So this is a clay-based, and when it comes to clay-based, we again look at the geopolymer, which is again a very, coming from the kaolin, and we modified kaolin into geopolymer, and then the geopolymer is again kind of, so the geopolymer is then modified with hydroxy, because geopolymer is not good at absorbing pollutants. So we modified it, and we do have data from neat to the even with the modified geopolymer. So the geopolymer, you can see, so when it is coupled with hydroxyapatite and 100%, this is HAP geopolymer, and this is geopolymer again HAP magnesium oxide with geopolymer. We do a lot of kind of alternation. We are tuning these materials with so many biocompatible nanoparticles to make it very super fast sorbent. So that's the strategy. So if you look at that, so now that's the one of those materials that we are. Not only that one, we do have 50 odd composites to list, but because of the time, and also we have characterized these things and published these things, that's why I just took it into consideration. And so removal of very high amounts of fluoride. So as I told you, the CKDU has a relationship with the drinking water concentrate high, with having high concentrations of fluoride ions. So the removal of fluoride ions from drinking water. So we look at we just kind of, see what is the superfast or the best composites out of all this, and we found it is hollow hydroxyapatite with MMT and hydroxyapatite sodium alginate. So we carried out these things, and we do have the adsorption of sodium alginate systems, and you can see now, I will go through briefly, and it is with the time, if you plot the removal ability, 62% can be removed, but it's not that fast though, but we are modifying it further. And this is adsorption isotherm with the hydroxyapatite. And for these things, and these are all technical terms. I'm not going to detail into that one. We are studying first. We are kind of optimizing the contact time, and then we are optimizing the best pH, and then only we are carried out isotherm studies. But don't have to show everything. So I can see now these are this 12 milligrams. If you look at the capacity, it's 12 milligrams per grams is being removed. So it's just a nice one compared to the existing data and with the other materials. And this is HAP with MMT, and this is again with, you can see the removal, 57% of the fluoride can be removed in 250 minutes time. Okay, right. So this is just a kind of a mechanism of anion absorption. This is, we are talking about the anionic adsorption, not only fluoride, we also carried out arsenate test. So the mechanism of anion adsorption mechanisms are, I think, well known to you. Because of the time constraint, I will kind of, if you do have any questions, we can talk about it later. And this is the removal of very high amounts of cadmium and lead from polluted water using, so we used HAP chitosan, HAP carboxymethylcellulose, HAP geopolymer. All these things were tested on the removal ability of cadmium and lead. If you look at the results are amazing, because you can see this is a super fast material. We published this data. So 30 seconds, within 30 seconds you can see how much of lead is removed that's a super fast. My PhD student Dhanushi had done this work, and it's a super fast material. And also we can see even chitosan, again within 3 minutes, it's almost 200. You can see that within 3 minutes, amazing amount of lead has been kind of absorbed. And these are the adsorption isotherm studies. And if you, this is, we just fit those studies into Langmuir and the Frenglich isotherm models to see which model which model it will fit, and then in order to see the capacity. So we compare this data, the lead absorption data with the reported data, and you can see that, these are the reported data with the other available materials. And I would like to take your attention. So the highest reported value of the removal of lead is reported by calcium hydroxyapatite, normal calcium hydroxyapatite. And amazing, you can see our results. It is 9009. So we is the first one to kind of publish this much of the material which can absorb this much of lead. And we published this data in one of the best journals international. So adsorption isotherms were, then we look at the same material to see whether it is good at absorbing cadmium as well. Amazingly, yes, we can see the same kind of results we obtained with cadmium adsorption. That's 30 seconds with calcium, with the chitosan-based hydroxyapatite nanomaterials. I'm sorry about these notations, but I have to use those notations. Right. So now we just carried out all these necessary analyses and kinetics to show to get the adsorption capacities. So this is the adsorption isotherms for cadmium with chitosan-based hydroxyapatite. And then adsorption capacities were just checked with the carboxymethylcellulose hydroxyapatite, and we can see again the similar results, like in the case of lead, were kind of we identified. And now again we did all these kind of kinetics data to get the adsorption isotherm, and then we see this is again marvelous materials and super fast materials to take out cadmium from water. And then this is the summary of the isotope model parameters. That is again with hydroxyapatite MMT composite. And you can see this is adsorption of lead. These are because we are looking at all possibilities to get the superfast hydroxyapatite, hollow hydroxyapatite HAP. I think the Veromi will discuss these things today in your presentation. You remember? No, okay, that's okay. She will present something else then. Okay, right. So you can see that again. This is a 60 seconds. Again, we are successful in this one because it's like within 60 seconds or 1 minute. The cadmium has been 80%, okay, close to 70% cadmium has been removed with hydroxyapatite, hollow hydroxyapatite, like modified with iron oxide nanomaterials. And this is the cation adsorption mechanism. As initially I think you're scientists, we know all about this one, but if you have any questions, we can do it later. So the removal high amounts of textile dye. Textile dyes is again considered as one of the carcinogens that is found in drinking water. So our materials are extremely good at absorbing textile dyes. So we checked the hydroxyapatite, chitosan, carboxymethyl cellulose, sodium alginate, and hydroxyapatite, hollow hydroxyapatite towards the removal of textile dyes. And amazing, this is the methodology in brief. And so what dyes we considered, and we considered these the removal of acid yellow 2R. That's a very famous dye which is being used in textile industries, and a lot of effluents you can see coming from textile industries rich with these dyes. The one is acid yellow. So then we applied our nanomaterials, and you can see within few seconds, all the colors really got faded, and you can see. Okay, that's one of the acids that we use. I think this is okay. Right. Let me see. No. Right. Okay, I'll go to that one. Okay. So this is the second acid we are looking at. Okay. If you look at this one, this is again a Conco red. It's a red color acid. That one is a yellow color acid. This is a red color acid. Okay. And then so this is again very carcinogenic, and then we have selected these two dyes because these are the more frequently used dyes in the textile industries. So we used our materials, and you can see amazingly within 2 seconds, 2 minutes, everything is get absorbed, and that's a microwave assisted and normal shaking. It took like 60 minutes, one hour, but with a microwave assisted, it just within 2 minutes, everything is gone, and super fast in absorbing. And so we again carried out kinetics for this particular acid, the dye, and we found 75 milligrams per grams is being absorbed, which is fairly high. And then, okay, this is some of the work that Tanushi did. That's to check the structural influence of HAP on dye adsorption. Because we are chemists and we are scientists, we want to see what structural features would enhance dye absorption. Right? So now for this one we took 4 HAP nanocomposites, and that's a normal HAP and we just synthesize using microwave radiation, and zinc doped, and magnesium doped, and sodium alginate. And we want to see the and we just check the porosities. According to porosity, BET isotome studies, the highest porosity is observed with the M3 system. M3 mean hydroxyapatite doped with magnesium. And the lowest is seen from the sodium alginate. Amazingly, when it comes to the dye studies, the M4 system, the alginate system, has shown the best adsorption. So we found it is not the kind of surface area which is responsible. It's like if there are so many if there's a polymer or a ligating atoms which can adsorb dye and have the catalytic effect to destroy that one, that would be the ideal. So the sodium alginate system is having not only the hydroxyapatite, but it has, even though it's the low surface area, So, but it has a better chelating groups, which is sodium alginate. I think that might be the reason to having this higher adsorption capacity by sodium alginate. And then we study use of drug-loaded HOP that's in biomedicine. And as Professor Rajapaksa mentioned, we know we are also looking at the, I think the Professor Suvan is there. I'm sorry. Good to see you. So, and also we are looking at the nanoparticles, and we are talking about the toxicity is still a question mark, but I said, hydroxyapatite is a very much biocompatible, so that's why we are looking at the hydroxyapatite for biomedicine. Right, so if you look at the use of drug-loaded hydroxyapatite for controlled and targeted drug release. So my student, Danusi, she presented the presentation in the morning. We were looking at the targeted drug delivery. What do you mean by targeted drug delivery? I think this is, when it has to be targeted to the site of the tumor. I mean, we are basically looking at the tumor-oriented or anti-cancerous drugs towards the tumors. So the tumors are having low pH values. The low pH, so if you can target the drug carrier to the sites where a drug can deliver at low pH, that is again, it's a targeted drug. We call it as a targeted drug delivery. So now, we are looking at the pH sensitive. I think a better explanation was given in the morning by Danuji. So I think I will skip these slides, and you can see, I will go to the results. Okay? And the results, if you look at according to the results, now we have loaded curcumin because, like other doxorubicin and the other also we are looking at the doxorubicin, 6-gingerol and the curcumin. Out of these drugs, 6-gingerol and curcumin, they are naturally occurring and, cancer drugs. And it has doxorubicin is having a lot of other side effects. So we are looking at the natural anti-cancer drugs. So we loaded curcumin. I'm taking only one example because she kind of delivered a good speech in the morning with all the other examples. So the curcumin is now, we loaded curcumin into the drug carrier, again based on hydroxyapatite iron oxide. And the loading, and then we wanted to see the releasing studies in different pHs. And when you look at the releasing studies, we found that the 90% is released at pH 5.3, and which is the 5.3 is relevant to the tumor sites. That's the pH which is there in the tumor sites. And compared to the other normal body, pH 1.4, and the release is much more less. So again the HAP, that's a kind of application of hydroxyapatite in biomedicine. Not only that one, we also look at the use of natural drug-loaded HOP nanoparticles to obtain more sustained antibacterial effect. So the antibacterial effect, because post-transplantation, and Professor Gamini Rajapaksa was talking about the prosthesis. So they are developing these prostheses, and sometimes they are developing it in hydroxyapatite, but there are so many other bones and everything that they are going to transplant. So the post-transplantation infections, bacterial infections it's a very big problem in medicine. And so the big other thing is, now if you look at these bacteria that are responsible for these infections, the Salmonella aureus is being identified as one of the dangerous species when it comes to bone infections. And these bone infections are very kind of, sometimes very painful, and it gives a big swellings. Sometimes you may have to take the limb, again the things out of the body to, it is because it is not compatible. So it's very important to maintain something, maintain some kind of having some drug to get the sustained release of antibacterial compounds. And when it comes to other antibacterial compounds, the available in the market, so they have to, they are the time, we have to have more frequent dosages to keep the the levels in the blood levels into the correct level. So I mean, you have to have some, if you can develop something which can have that effect in a prolonged way, so that would be ideal. So in that case, you know, we also just check our drug loaded. Oh, I'm sorry, I think I can't see the other one. The animation has gone here. Okay, right, we are having, because what we did was we used the Salmonella aureus as a bacterial strain, and then we just applied whatever the drug-loaded hydroxyapatite inoxide nanomaterials, and we carried out the hydroxyapatite with curcumin and hydroxyapatite with 6-gingerol. They are both naturally occurring antibacterial and even tumor substances. So they are antibacterial effect. Then we just studied their, now you can see the inhibition zone comparison. Control versus 6-gingerol loaded and hydroxyapatite inoxide nanomaterials, and curcumin loaded hydroxyapatite inoxide nanomaterial. If you look at this graph, now if you, this is the diameter of the inhibition zone is in the y-axis, and this is day 1, 2nd, 3rd and 4th day is in the x-axis. You can see now this is the control gentamicin. The effect is gone at the 3rd day and no antibacterial effect at all. I mean, it would have been nice if I can take this one to the top, but you can see now this is based on the experimental results we plotted. And then if you look at the other 6-gingerol loaded and curcumin loaded hydroxyapatite inoxide nanomaterials, you can see their effect is not that pronounced in the day 1 and day 2, but it's just sustaining. Even up to 4th day, it is sustaining and it is giving a better effect. And this, so you don't need frequent dosages of, and because then bacteria get kind of, you know, resistance to those antibacteria, antibiotics. So this is again successful, and yes, and we publish all our, findings in journals like Asia Advances in 2016, and then this is the recently metal and polymer mediated synthesis of porous crystalline hydroxide nanocompounds for environmental remediation. This is a recent one, still in the press, and it is now in the web. And then again biocompatible curcumin bi-coated antibacterial activated carbon for water purification. And this is again with the hydroxyapatite with granule activated carbon. And this is the pH responsive control is anti-cancer from sodium alginate hydroxyapatite system. And so with that note, so I would like to acknowledge, first of all, National Science Foundation for giving me yes? Oh, National Research Council, I'm sorry. Yes. I'm looking at this because sorry about that. National Research Council, yes. I should thank National Research Council for funding my research, and the Royal Society of United Kingdom, because we got collaborative projects with University College London, and then again it is connected to University College London, EPSRC College the funding, and University of Colombo, that's my favorite place, and SLINTech, of course. They are the wonderful people behind the scene because they do all the characterization. Thank you very much, Damayanti and everybody. Thank you so much. And Nisan Sala and Induni, yes, you're doing a wonderful job. Thanks. And my PhD students, all my 11 PhD students, I can say everybody is here. Wonderful to have you. Without you, I can't present this one. Thank you very much. And my collaborators, and for everybody for listening to my talk. Thank you very much.